So let's begin with the third lecture by Harry, and I see that there is the cure, the aqua machine.
No, this is actually
No.
these
Oh, this quick
yeah.
stimulation.
The question, do you have the clicker? No, no.
Maybe it's over there. You have to be done.
Oh, yeah, it's plugged in. Okay. So last lecture, I told you a little bit about some of these tools that have been super useful. So I'm just going to do a very quick demo with some of them, just to give you a sense, show you some tricks that are commonly used. And this is something that we, like zooming in. And this is something that we regularly use in our research to optimize circuits. So here what I'm going to do is just to verify the correctness of a T-gate circuit. So let's see how to do that. So I want to verify that the gate does an actual like T-gate and not just prepare a specific state. So in order to be able to do that, I'm actually going to create a bell pair here. So this is 2 qubits. We can like look at its density matrix. So we see that it's yeah, I guess this is, you can verify that this is the correct density matrix. And so this is a bell pair that we've created. And the reason that we do this bell pair is so that if we do a gate on this bottom qubit, we can verify that whatever basis it's all doing the correct operation, thereby verifying that it's the full unitary. In quantum information, this is also called the Troy-Jamakowski isomorphism. Okay, so we want to do a T-gate. So as I think actually Christian had the circuit earlier, but unfortunately it got erased. So I need to do the slide now. Okay, so we have this T state that we prepared. We can look at the block sphere here. Okay, it's pointing along this 45-degree T direction, so that's good. And then we do D naught. And then this is the part that one always needs to spend a little bit of effort getting right. The feed forward is often the one that needs a little bit of thinking. Okay, so ideally what we want here is for the T-gate to have been applied here. So how do we check that? What we can do is we undo this T-gate, and then we do another, like, basically disentangle the 2 qubits, and they should come back to 0. So in this case, they do indeed come back to 0. So that's how we know that it's done correctly. Okay, makes sense so far? So quick verification of this. Something that you can quickly play around with is instead of doing the C naught this way, you can actually do the C naught the other way. So all of those we need to fix. Okay, but now we're not getting the right thing. So why is that? That's because the feed forward actually needs to change. This is yeah, this is the correct one because both of these are now 0. Okay, so you can see kind of how you can really very quickly iterate on things and like play around with different circuits, get good intuition. This is how people like Craig Gidney come up with their crazy circuits, and later on in the actual part of the talk, some of the circuits I'll show you are also derived from this. So the other tool I'm going to show you is this tool called which is more used for error correction workflows. So this is actually a repetition code circuit. So you can see you reset all of the qubits here. and you can go forward in the layer. It's very nice because you directly see the geometric layout of the different layers. And yeah, I'm pressing the hotkeys E and Q here. That's how I'm moving between them. There's a lot of hotkeys that you need to learn with this unfortunately. But yeah. Okay, so yeah, so you can like play around with circuits. They also have some examples. So you can do like the surface code, track how certain things propagate through the circuit. You can see here that you're tracking the propagation of some Pauli operators. So again, a super useful tool in practice. So I just wanted to show those because I think those are actually like probably some of the more useful things in practice. Okay, and now I'll move on to the actual content of the presentation. So we already heard a little bit also from Christian about some of the basic building blocks of error correction. So today in this final lecture, I'll be focusing on one of our recent experiments done at Quora of experimental demonstration of logical magic state distillation. So as we know, quantum computers can hopefully be quite useful for a wide variety of applications. But the problem is that the error rates that we want for like Shor's algorithm or chemistry typically are around something like 10 to the minus 12, whereas the physical error rates that we have today are something like 10 to the minus 2 to 3. And so there's this very big gap that we need to bridge through quantum error correction. I already showed a little bit of some of this stuff on Monday, but there's been a lot of exciting work throughout the community, really starting to build towards these early error correction platforms with neutral atoms, trapped ions, supernutting qubits, and I think it's broadly captured a lot of interest. And so I think kind of this really motivates thinking about what types of key building blocks should we start exploring and start implementing in the experiment. And so in particular, what I'll be focusing on today is first, again, just giving a very quick review of the neutral atom platform. Most of these I talked about on Monday, but I'll be focusing more on the aspects relevant to error correction. And then I'll tell you a little bit about the new magic state distillation results. So quantum computers have been around for a little bit with the early NISQ processors, but why is it that it's only in the last really year or two that we've started seeing implementations of error correction? So one of the challenges is that you need to have many physical qubits encode each logical qubit. I think I briefly touched on this towards the end of my lecture on Monday. But what this means is that if you have directly one wire controlling each qubit, that's quite a bit of overhead, and that's why it's taken some time for this to really become possible. The second challenge is that information in these logical qubits, in order to not be corrupted by local errors, the information has to be delocalized in some way. And so that also causes some challenges because when you want to perform gates, you often now need to look for more structure in order to allow you to do those gates. So kind of the strategy that was taken in the neutral atom community is really to develop this dynamically reconfigurable neutral atom architecture so that you can address some of these challenges. So I already talked about this platform. I won't go into too much detail again, but just show this movie again to highlight a few things. So first is that you can dynamically move the qubits around. So this gives you a lot of flexibility in terms of what types of circuit, what types of connectivity. But equally important is the fact that these qubits are being moved in a grid in parallel. So we're moving all of these qubits together. And what this means is that we really are using much fewer degrees of control compared to like an arbitrary pattern. So here, all of this movement is just being controlled by two wires coming into the system. And that's how we're able to execute pretty complex motion. Okay. And so what this allows you to do are these transversal logical gates, which Christian also talked about just now. So you take these code blocks, you interleave them, you shine a global laser, and very nicely, you're able to implement a logical CNOT gate. So this in kind of a single stone kills two birds. We both get our logical operation. Now we're able to do a logical CNOT with a pretty natural operation that we have access to, And also we've been addressing this wire challenge because we're doing all of this movement in parallel and interleaving things in parallel. And so one can really start probing some of the basics of error correction. You can probe the improvement of the entangling operation with code distance, which is what you want to see, right? You want to see that as you increase the system size, the system gets more and more protected. And so we do see this type of suppression of the logical error rate as we go to larger sizes. And so this really provides us with some building blocks for which we can now start exploring like really algorithm level building blocks. Any questions so far? This was a very quick review of what I talked about previously. Okay. So let's dive into distillation. So starting to think about building blocks, of course, it's useful to ask what is the most common building block? And if you look at some of the early papers in the field, this is a pretty famous surface code review from Austin Fowler et al. You'll see quotes like this. So computational qubits comprise less than 6% of the quantum computer footprint. The rest of it is this thing called magic state distillation. Now, recent improvements in magic states have, of course, changed the balance of these numbers. I think latest state of the art is probably somewhere around 20 to 50% of the system is being used for magic state distillation. And that cost balance might continue to change as different schemes get discovered. But still, nonetheless, this is seems to be a pretty important subroutine, at least as a basic idea. And so just to again review this concept of magic states to understand what this magic state distillation is. So we already heard a little bit about universal gate sets allowing you to implement any quantum computation. I think Christian briefly mentioned the Easton Kneel no-go, in which you cannot have a universal transversal gate set within a single code. And so because of this restriction, the typical approach is to prepare a magic resource state, which then through this teleportation circuit that I think was also on the board earlier and what I was showing in the quirk example, allows you to implement the T-gate. And the magic state, again, is pointing along this 45-degree direction between X and Y axes. And so essentially, if you have this magic state, then you can use transversal Clifford gates for everything else. So trying to prepare magic states is not new. People have done a series of pretty impressive experiments to try to prepare them. So this paper is from IBM, this is from Innsbruck. So these two use various small gadgets that essentially use an extra so-called flag qubit to help flag the errors and try to prepare a magic state with a quadratic error suppression. There's also this continuum paper that just directly encodes one. Generally speaking, these codes actually could make a lot of sense as the first step of preparing them. But if you want to get to better and better logical error suppression, then typically the schemes become quite a bit more complex when you go beyond the lowest distance. And also they start to have pretty quickly decaying success probabilities. Of course, in practice, the success probability, even if it's 1%, might actually still be okay in practice. And that's what these new magic state cultivation papers and ideas are essentially kind of building on. But in general, just using this directly at the physical level, you do run into some challenges or constraints like this. And so therefore, one strategy for really overcoming this is to do this magic state distillation, in which you can now do multiple stages of refinement. So the idea here is that we have some low fidelity magic states. In this case, it's actually pointing along the 111 direction instead of this 45-degree direction. This is for the specific distillation factory that we're using. You can do multiple rounds of this purification process, which allows you to get to arbitrary target fidelity. And the key idea here is that you're running some outer error correction code. So you encoded your data into some inner error correction code that protects most of the operations within this distillation factory. But then in order to purify the magic state, we put on top of it another layer of an error correction code. And so that error correction code might be the 1513 Reed-Muller code that Christian talked about, might be an A32 code. In this case, it's a 513 smallest error correcting code. And that one will be the one that helps us purify the magic state. Okay. Does this basic idea make sense to people? Okay. So magic state distillation has also been experimentally implemented, but only on physical qubits so far. So this is a paper from Continuum. This is actually a pretty early NMR paper trying to implement this 5-qubit distillation circuit. In both of these cases, because it's directly on physical qubits, you end up being swamped out by gate errors. And so you actually, in the actual regimes of operation that you would actually care about, you wouldn't see an improvement. So that really highlights the need to try to operate it with logical qubits. So these circuits for distillation, if you just like take one from some of these older papers, they look pretty complex. They involve many logical qubits, many logical gates. Often some of these gates require conditional feed forward. So this is actually a pretty high demand on the experimental capabilities. And so when we were designing the experiment, we really tried to do it in a somewhat architecture co-designed way to minimize the resources that we need to use and to make it as easy of an experiment as possible for the hardware folks. So let's take a look at some of the details of this architecture design. So the first step is, of course, you want to choose what data encoding you use. How are you going to just, even without considering the distillation, encode your logical qubits? So here we chose the 2D color code. There's a distance-free version. It's drawn a little bit differently from what Christian had there, but you can convince yourself that you can deform them. The reason we draw it this way is because we're trying to emphasize that it's part of a larger family. So we're using this square octagonal family, and we do both the distance-free and distance-5 surface code, color code within this. So now that we know what logical qubit encoding we want to use, the first step will be to encode a single physical magic state into a logical qubit. So we'll do some encoding circuit that I'll go into detail in a moment to try to do this first step of the operation. And then after that, we'll be doing some operation that comes from this distillation code. In this particular factory, what's happening is that this circuit is actually an unencoding circuit for the 513 code. So what does this do? If you have some initial thing here, then it will map the logical qubit onto this output. So now it's just a single rail instead of 5 rails. So previously, let's say you had like a five logical qubit, outer logical qubit, right? So there's 2 layers. So the outer layer had 5 logical qubits. This circuit will essentially output that kind of actual logical information into here. And these 4 will be the stabilizers of that 5-qubit code. So we've essentially done a mapping such that we kind of map the information out. And these stabilizers, if you measure them, then this actually also, right now, in this circuit, would project the code, the original input state into some subspace. And so that's how we're able to get both the distillation output and be able to check for errors in the moment. And then finally, based on the results of those 4, we'll do some conditional operation, either discard the state if we saw some signatures here, or let the state through if we determine that the result was correct. Any questions so far? Okay. So the first step is to find a good encoding circuit. So the best one that we were aware of for encoding an arbitrary state was this one by Meyer et al. So if you look at it, this one involves at least 4 layers, 11 entangling gates, which is reasonable, but still, it would be nice if it was a little bit better than this. For example, the previous experiments at Harvard encoding a special state into the color code only needed to use 3 layers. So certainly we would ideally hope to be able to at least push that to 3. We also couldn't find any explicit references for encoding d equals 5, although this is something that there are generic recipes. So there are generic recipes for doing that encoding, but again, those generic recipes will of course be a little bit more costly than you would want. So then basically what we did was to try to just optimize really these encoding circuits. So these are the circuits that we ended up finding. I should highlight the contributions from Sunny and Casey. For these circuits, particularly Casey did a lot of heavy lifting. Essentially, for the distance free, it was just done by hand, literally using the quirk tool that you saw earlier. You just like keep jiggling things around until you get the right thing. So very, very systematic procedure. And then for the distance 5, it was a little bit too painful to do that. And so what we ended up doing was to use a heuristic guided search. So I guess the reference for some of the basics is here, but essentially you write down the stabilizers as a matrix, and then you do row and column reductions, and then you use some heuristics to guide a computer to search through that space. And so what we ended up finding is that for the d equals 3 code, we can do now only 3 layers, as you can see here. And for the d equals 5, it's only 5 layers. We think that this is optimal, although we haven't directly confirmed this. And also then following this, we also optimize the atom movement, and I'll show you some movies of what exactly it looks like later on. Okay. So the next step is we also want the distillation circuit to be very good. So if you look at the existing papers, for example, this one from this physical distillation experiment, it actually has quite a lot of gates. This one has 17 2-qubit gates, and they're also done in a pretty sequential way, which is not very nice. So fortunately, if you like follow social media, sometimes you just get exactly what you need. So in this particular case, actually this, you might notice that this was a year before we did the experiment. So really, it's important to stay prepared. Craig Gidney just randomly had this thread of tweeting like different numbers of CZ gates to exactly do the 5-qubit encoding circuit, which is exactly what we need. We just run that in reverse, and that's our unencoding circuit. Of course, later on, like we were able to find good encoding circuits for these other codes. So I'm sure if we had to do it ourselves, we would have been able to find a very similar one. But yeah, it's just nice to have most of the answer given to you. And then also, speaking of that, after our paper, Craig had a tweet about it. Usually in the error correction sphere, when you put out a paper, you're always very nervous what Craig will say on Twitter about your paper. Fortunately, he said something good about our paper, so we're very happy about that. Okay, so this particular circuit still uses 4 entangling layers. So we did some like quirk tweaking to really minimize both the local rotations, the number of layers, to optimize it to 3 layers in the end. Yeah.
Can you give a little bit more information why the encoding is the circuit that I want? If I look at it from the other side, I have a very good magic state.
Yeah.
Some like states in the product state. But on the other side, it's not like I have a very clean like 513 code. I just have like product state of different states.
Yeah, so that's the funny thing here. There are 2 things happening in parallel. When you measure the distillation syndromes, it actually first projects it into the code space. And so originally you had this unentangled like 5 logical qubits. And then it's actually through this circuit and projection that you like end up being projected into one particular subspace at the beginning.
Oh, so is it fair to then think of that this circuit effectively maps the stabilizer of the 513 onto the local Z operator?
Yeah,
there.
exactly.
And that operation in fact is going to be a 50-50 coin flip, but when I get all the measurements at the right place, I know that I prepared the right state.
Yeah, and in practice, the weights are uneven, so there's a 1/6 chance of projecting.
Thanks.
Yeah, this factory for that reason works a little bit different from the usual ones. So usually you wouldn't have this subtlety, but it's present. Yeah. So let's do our favorite thing, look at movies of what exactly this looks like. So we're doing encoding right now. We're doing this is the distance 5 version. So you can see these different layers. We do these symmetric motions and then putting them back so that we can echo them effectively. Yeah, you can see that it's really banking on this parallelism of control, right? All 5 logical qubits are getting encoded in parallel. And then when we do the distillation circuit, as you see right now, each row is a logical qubit. So when we do transversal gates within this distillation, it's again a very parallel motion of just taking one row, putting it on top of another, and then doing the circuit that way. And we also run 2 copies of D = 3 in the actual experiment when we're doing that part, just to get higher data rates. Great, so I told you a little bit about some of these basics. Now let's take a look at how exactly this distillation works in practice. Before that, are there any more questions? And I should, of course, highlight the experimental team who are really primarily working on this. So Pedro, John, Nikki, and Sergio. So the first thing we want to confirm is that the encoding is indeed performed the way we want it to. So here what we're doing is putting in different states in the XY plane and then performing tomography along the XYZ direction in order to confirm that we have indeed prepared the state we want. So you can see that there's this characteristic oscillation, which is very nice. And then we can also evaluate the injection fidelity of the magic state across 10 logical qubits in parallel, checking what level of fidelity that we get. So here there are several different bars. This is just if you just take the raw data and look at the logical expectations, but we can also run error correction or post-select on no stabilizers being flipped. So that's more like error detection. And we see these different levels of fidelity. The most relevant one is the error-corrected one, because later on, we'll be comparing it in a setting of like having a factory and then having an output qubit. So we'll be focusing on this error-corrected number. So next, now that we've encoded, we can run this distillation circuit. And here there's an interesting trade-off that you can actually do. So magic state distillation, remember we're trying to prepare a resource state. So we run some operation and then we get some state out and we get to choose whether we keep this, state or not, right? But because it's offline, it's not in the main computation, if we're not happy with it, we can go and repeat it again. And so here then, you actually you're usually a lot more willing to do post-selection because each post-selection can be done in a repeat until success fashion. So if you had, say, like 5 of these T gates, instead of the probability of success multiplying and being P to the 5, it actually is like linear in P, the amount of cost that you pay, because you can repeat until success. And so because of that, one actually might be willing to be a little bit more stringent on this post-selection. In particular, when we measure these logical qubits, we have both the logical information, but we also have the stabilizer information of each of those logical qubits. And because these transversal gates that we're doing are really propagating information of errors between these qubits, you would imagine that using those stabilizers and whether you had a lot of stabilizers flipped would actually be an effective way to help make sure that the output was as good as possible. So in order to be able to tell which ones were the good ones and which ones are the bad ones, then we need to be able to develop methods for decoding and flagging errors. So that's what I'm going to tell you a bit about next. So the basic idea here is that we have this logical circuit that we're running. And remember, I told you on Monday that for the decoding problem, you're given some input about the circuit. You're given from that, you deduce how errors trigger syndromes. And you also have this table of what the probability of errors is, right? So trying to solve this particular problem. And so when you have multiple logical qubits, really the same recipe still applies. And what will happen when you apply that recipe is that if you had a physical error on one qubit, which propagates through a transversal gate onto another qubit as well, essentially this will just become part of your description of this problem that you set up. And so it's still the same recipe. It's just that the problem that you're trying to solve is now a little bit more complicated than before. I mentioned the other day also that that really using these types of ideas, one can reduce the number of syndrome extraction rounds to only a single round per operation. This is also highly connected, and why we can really do this. Yeah, and the space-time decoding idea is essentially what I said, that the formulation in the end is all the same. So how exactly do we do that? We have some rough sense of the general recipe, right? We have our observed syndromes, and we're trying to find the most likely error that explains that. So what exactly can we do? So the first decoder that we had, both of these are, by the way, brute force decoders by usual standards. So the first one is like a brute force decoder that is a little bit less brute force. So what you do is you construct this detector error model. This detector error model is essentially just like one way to specify this decoding problem in this format of like parity check, effective parity check matrix and weights. Then you just rewrite this into an integer programming problem and just give it to some like solver that can do it reasonably fast. So what this one does is it identifies the individual most likely error. So it says, okay, there are many possible errors that could have happened. Which one is the most likely one? And I'll just say that that's the one that happened. But actually in quantum error correction, there's oftentimes degeneracies. So just to give a concrete example, in the surface code, if I saw two syndromes somewhere, there's many different paths that could have connected them. And so there are many possible errors that all lead to the same syndrome. And because of that, there's actually also an entropy factor associated with, okay, even if this one, if this particular error assignment was the most likely error, perhaps another error assignment might have a higher entropy factor and is actually more favored. And so this is what people call maximum likelihood. So this is, if you had an accurate error model, this would be the ultimate limit on what you can do. And here for the d equals 3 case, we can actually do this. Essentially, we just brute force sample a bunch of like shots in simulation. And then we just make a big table and just see like for a given observation, what's the most likely possibility in that table. So both of these, as I mentioned, are somewhat brute force decoders. And so an important area in the future is really to come up with faster and more accurate decoders. Any questions about decoding? Probably a lot of you are seeing this for the first time. So I think if there's anything that didn't make sense, please stop me.
Another question is like, so your process has like a physical layer, the logical layer of the state, and then another layer above.
Yeah.
So when doing this correlated decoding, is it kind of like just at the physical level integrated over the entire layer, or just the physical levels that then inform the errors on the top and then?
Yeah, this one you can think of more as the physical level and the first logical level together. And then the top one will be applied after this. So Earlier on, I said there's this opportunity to also use these stabilizer results to further improve the reliability and confidence of decoding. So how do we determine the confidence? One example thing that we can do is we run so we had the circuit over here, we run our decoding, we decide that the measurement results on these 4 qubits are 0001, and we have some like likelihood, but then we can rerun the decoding and just force other outcomes. So that gives us a comparison of what the most likely error for each of these configurations are. And essentially, by looking at the gap to the second one, we have a rough sense of how confident we should be about our assignment. If this gap is very large, then we're pretty confident that we chose the right thing. Whereas if this gap is a lot smaller, then maybe we're a little bit less certain, and so we might be more inclined to throw out that shot. So using these tools, we can examine the resulting fidelities. So here, what we're doing on the x-axis is really changing how stringent we are with this confidence screening. So on the right here is we just accept all of our error-corrected decoding results, and we don't do any of this extra filtering. There is still a total accepted fraction that is finite. It's about 12%. This is because the factory itself has this 1/6 factor to start with. And then on top of that, then as we apply more and more filtering, we'll see that the output magic state fidelity on the y-axis gradually gets better and better, ultimately reaching around 99.4% compared to the 95.2% input fidelity. And there's this continuous trade-off that you can choose where to sit at between how much post-selection, how much flagging you're doing with this extra stabilizer information and what your output fidelity is. Does this make sense? Okay. So we can also compare both of our decoders. So we have this most likely error decoder that I was just showing you on the previous plot. The maximum likelihood does perform a little bit better. There's a few features here that we actually still don't fully understand where exactly it's coming from. Yeah, but basically, yeah, so this is kind of roughly what you see. One thing to maybe note here is that there's a slightly larger gap overall on the right half of this. And one can maybe roughly understand it from the perspective that when you're pretty confident about the assignment, probably the entropy factors don't matter so much. It's only when you're at the borderline that the entropy can push you to choose one versus the other. So that's why the fidelity gap is slightly larger on the right half compared to the left half. So to further verify the performance of this magic state distillation factory, what we can do is really try to just directly add input errors and probe how the factory responds. So here we're doing complete stabilizer selection. So we're applying the most stringent filtering, and then we're looking at just how the factory operates on this logical degree of freedom. So on the x-axis here, we're making the factory, the input fidelity worse and worse. And what you see is that the acceptance rate of the factory immediately starts responding. When we add in a little bit of error, there is a linear slope here, which means, indicates to us that the factory is likely rejecting single input errors. But if we look at the output fidelity, initially it's a little bit flatter, roughly consistent with the quadratic curve. And so this is also consistent with the fact that for the output, we get a quadratic error suppression and 2 input errors are needed in order to get an output error. Another thing, of course, is that we're always above this diagonal line, which is the break-even line. And so we do see that the output fidelity is better than the input fidelity. Yeah.
Why is that the acceptance rate just so that's like 0.16 even at fidelity very large?
Yeah, so this is what Francisco was asking earlier about the operation of this, where there's a projection into the into the like code space happening at the same time. And so even if everything was perfect and there was just like the natural quantum projection, you would already have like a 1/6 acceptance rate. Yeah.
Does that do the post-selection?
Yeah, so this is due to this projection causing you at this outermost level to have an extra layer of post-selection. We can also probe this for different distances. So we have distances 1, which is just directly using physical qubits. Distance 3 is this distance 3 7-qubit color code, and then distance 5. And what we see is that the input fidelity gets worse with the code distance, which is roughly what you expect because we're just injecting this single piece of information into larger and larger things, and there's more noise in the process of this adding it in. But we see that once you use this distillation and use suitable flagging, then the fidelity of the output improves compared to before. Right now, this acceptance rate, total acceptance fraction, is still going down in order to maintain this. But we estimate that if we could improve the gate fidelity by a factor of 2, then we would be able to consistently have this gain without this decrease here. So right now, our gate fidelities are quite not where we want them to be. Okay, so I told you a little bit about how with these neutral atom quantum processors, we can really start exploring a little bit some of these early fault-tolerant logical algorithms. I think on Thursday, I guess tomorrow, Misha will be telling you a little bit more about some of these works, particularly this earlier first Harvard experiment with up to 48 logical qubits. But today here, I've been mostly focusing on this key subroutine of doing logical magic state distillation, which, as we've seen, are quite important as a subroutine. Yeah, we've been able to start to probe really the basic operations. But I think here we're really only looking at the beginning of preparing these magic states. So there's also a lot of exciting new ideas in the field. This so-called magic state cultivation is a nice, neat new way to really use your post-selection and optimize the circuit in a very clever way. But I think ultimately experimentally exploring these things and see what works well, what doesn't work well, will be really important as we go forward in this era of early fault-tolerant processes. So I think it will be really exciting also in the coming years to continue exploring this. So with that, I'll thank my collaborators here again. So on the experimental side, I already mentioned the Gemini team. On the theory and software side, there were also a lot of contributions from these folks, particularly Sunny, who was an intern with me last summer. And then also from the Harvard Atom Array team, we had a lot of useful technical exchange in the process of building these. Great. So thank you for your attention. More questions? Yeah. I'll also be heading out after this. So yeah, so right now is a good time to ask any. Yeah.
Yeah, it's a broader question, like you emphasize this distillation, you mentioned this cultivation, you kind of alluded to this cultivation. Can you kind of give a bird's eye view of kind of trade-offs and of these different approaches?
Yeah. So cultivation appears to work well when you have very low physical error rates. Very low meaning like below 10⁻³ is where it like generally starts to kind of outcome peak values. Essentially there what's happening is that you use post-selection pretty heavily, and you're using post-selection in an exponential way. So it's really like as you increase the error rate, the success is kind of scaling at a pretty high power. But if you, for example, even if you had an exponential, right? If you sit early on in that exponential, you can still get like 50% success rate. So that's basically kind of the trick, that although you're paying quite a bit in post-selection, you're not paying enough for it to kill you yet. As you go either into even lower target logical error rates, or if your starting physical error rate wasn't quite as good as you wanted it to be, then then you start wanting to add in a little bit more logical level stuff. And that's when you start doing distillation. For code switching, at least in terms of current estimated numbers, oftentimes people haven't quite been able to compete with magic state distillation or with cultivation. The main reason is that existing analyses haven't really utilized these post-selection things very much, which are used in both distillation and cultivation to get suppression. And so I think it's still like actually pretty interesting to analyze how far one can get, also with new 3D codes. Yeah, but I think the numbers still haven't been fully worked out. Yeah.
Yeah, so the acceptance rates versus coexistence.
A little bit down.
The acceptance fraction versus the coexistence. How do you, it's almost linear, like you have a feeling how it would look like.
Yeah, I guess maybe one thing also to mention is that this point was actually not full post-selection, so it wasn't post-selecting on everything. The reason being, if we post-select on everything, then this error bar would have been even larger. So I think it's somewhat of a coincidence that this happened to be the case. Yeah.
So like the fidelity is like large code testing, is it also the same reason why the fidelity is dropping for the magic state still? For magic state after at code distance 5?
Yeah, I think it's a mix of that and then also the input fidelity getting worse.
You showed that there's this quadratic rise in the fidelity. Yeah. I did not get, is it like, what's the intuition that it should be like a quadratic rise or quadratic suppression?
Yeah, so essentially, if you only had a single error, then that would like cause your factory bit to flip. And so that would just get rejected by the factory. Whereas if you had two errors, then it could like flip and then flip back and then pass the factory test. And then it's in your output. Yeah, so that's why it's a quadratic.
Any other questions for Harry? Generic question. Both you and Christian have shown that, you know, one of the iconic features of these neutral atom arrays is that you do gate operations with moving the qubits. So can I think of this as a sort of a speed limit of the processor, or if so, how would it get better?
Yeah, definitely with the current implementations, this does impose a certain speed limit. Of course, because of at the error correction level, we have these transversal gates that speed up the logical clock speed. The gap isn't quite as large as what one might naively think, just based on physical numbers. But nonetheless, it would still be nice to speed them up. There are various different proposals that people are exploring. I mean, certainly, if you could trap the tweezers deeper, then you can move faster. I think the moves can also be optimized quite a bit more than currently. Yeah, I mean, there are a lot of theory proposals about like bang type, kick it and then like catch it. People haven't really tried that in experiment. There's certainly a lot of details that would need to be figured out for that to work, but it's not impossible, I think. And then also there's various tools that people have for also doing more local control. So you could also imagine maybe some parts you do these movings, but then other parts you're using a little bit more local control.
It's just a question clarify that I understand the purpose of doing that. So the magic state distillation is kind of, I want to have my answer of qubit compared to that magic state for implementing
Yeah.
So currently from this experiment, it seems like you use 5 logic qubits, and this is the latest one.
Yeah.
That is really good.
Yeah.
And which means that we're generating one answer of qubit, and it's really good with no like
yeah.
physical qubits to do that.
Yeah.
How do you envision the scalability of that?
Yeah, so actually here it's even worse because you also have this 1/6, so it's actually 1 in 30 effectively. In practice, people use a little bit more efficient ones. So 15:1 is the most common one, but then actually I think usually what people would do is you first do 15:1, and then you use 8 T-gates to prepare 1 CCZ. So you effectively like, and then 1 CCZ roughly can catalyze 2 T-gates. So effectively you put in 8 T-gates and you get 2 T-gates out. So that, I think that ratio is like maybe when we're actually operating this in practice, where we'll go.
Questions? Then join me in thanking.